I am Professor Kurdish, your instructor for this course, and this is Chapter 19, Vibrations and Waves. Let's get started. So, to talk about a waveform, let's first talk about the characteristics of what we're going to be dealing with when we're talking about waves. So, imagine we've got a marker that's attached to a weight. It's bobbing up and down on a spring, and the marker is marking a piece of paper that's moving continuously towards the right. So the shape that's actually drawn out by the marker on the paper is the waveform that you see there. That pattern is what we call a waveform. The mathematicians would look at that and say that's a sinusoidal wave, because I can describe that with a trigonometric function called a sine function. Of course, trigonometry is beyond the scope of this course, so we're not going to go there. But we are going to go into evaluating some characteristics of the waveform. And the two most important that we're going to be looking at is the wavelength and the amplitude. So first, the wavelength is the distance between identical points on the waveform. So if I took my wavelength here, I've got two of them that are marked out here. It's actually the same distance. You just need to make sure that whatever point on the waveform you use to start your measurement, you have to find the next successive identical point. So here this is really easy. We're looking at wavelength from the top here, which is the crest, to the next top here, which is the next crest. So from crest to crest, there's my wavelength. I could do the same thing going trough to trough. So if I go from this low point, which is a trough, down to this low point, which is a trough, I get the same distance. That's also wavelength. This wavelength that they're measuring here, where we're looking at, this isn't a crest or trough, it's somewhere in between. You might think, well, why is it that we're not using this point to measure the wavelength with? Well, that doesn't give us the same distance. And that's because this point is not identical to this point or this point. Reason being is, if you imagine this marker as it's traveling along this path on the paper. So it's marking out this shape on the paper as the paper is moving towards the right. So as the marker is traveling this path, when it gets to this point, the marker is actually going in a downward motion. When it comes back around and gets to this point, it's going in an upward motion. So this point and this point really aren't identical points on the waveform, because the marker is traveling in different directions. In order to be going back down, I have to continue to come back and come all the way over here to this point. Now the marker's going down again. Another way to look at that is if I actually took this portion of the waveform between the wavelength ends that I'm using for my measurement, I get a complete form of the wave. If I use this point, I'm only getting a portion. So I only get this portion, or I get this portion, but I'm not getting the whole form of the wave. This is the set pattern that's being repeated over and over again. So, looking at identical points for measuring your wavelength, I always find that it's easier if you just make it easy on yourself. Just use two high points, two crests, or two troughs, two low points. Just keep it one or the other, and that'll keep you safe when you're actually calculating out your wavelength for your distance. The other characteristic we want to look at right now is the amplitude. The amplitude is the distance between a crest or trough and the baseline. You'll notice that the waveform mirrors itself across the baseline. Now the baseline is that dashed green line that you see running through the middle of the wave. And if I take this shape here that's on top of the baseline and flip it over, then I get this shape right here. So it's mirroring itself as it goes along and travels along the direction of the baseline. And the distance between the baseline and the crest is the same distance between the baseline and the trough. So again, one or the other, doesn't matter which, you'll get the same distance either way. Let's go ahead and work an activity to practice these concepts that we just learned about waveforms. So in your workbook, you're going to find a waveform with some measurement bars beside it. And for the purposes of this activity, let's just imagine that these measurements are giving us units of nanometers. So we're measuring, really technically, we're not looking at nanometers, are really, really small. But let's just assume that the measurement bars are giving it to us in nanometers. I want you to answer the following questions. So the first question is, what is the amplitude of the wave? Second, what is the wavelength of the wave? And third, if the visible spectrum corresponds to wavelengths of 400 to 700 nanometers, would you be able to see this waveform? So go ahead, stop the video here, work on these questions, and then when you get ready, come back and we'll see how well you did. Okay, let's see how well you did with this. So here's our waveform, and we've got the measurement bars above and beside it. We're going to use these to measure our amplitude and wavelength. Now, as I said before, looking for the amplitude, just do it between crest and crest or trough and trough, and just do it that way, just play it safe. For the wavelength, it's often easier if, well actually that's what I'm saying for the wavelength. For the amplitude, you want to look at the vertical distance. So, just pick a crest or a trough and get the distance there. So the first question there about the amplitude, if I want to say, I'll take that first crest there on the far left. Just say I use that. So the distance between the high point there, which is the crest, and the baseline, which is the line in the middle, that's 140 nanometers, because the baseline is about 160. That crest is there at about 20. So yeah, 140 nanometers. Now, if you got something close to that, you should be good enough. The wavelength, again, we're going to measure from crest to crest. But, I didn't have to measure the amplitude using a crest. If I wanted to use a trough, let's say I use that first trough there on the left, I could do it that way too. So the 300 is the low point, 160 the baseline, subtract the 2 out, I get 140. So it doesn't matter how I do that. If I use the next two crests to say for my wavelength measurement, I'm going to get 220 nanometers out, because the one is about 500, the other is about 280, so that gives me 220. And, I could use two low points, so if I wanted to say use these two troughs, I could get the same thing out. It's about 845 for the one, 625 for the other. You can see, subtract those out, I get the same number, 220. So 220 is my wavelength. Now, with that wavelength, would I be able to see this waveform? Well, the visible spectrum we were given was between 400 and 700. So that means the wavelength has to be between 400 and 700 nanometers for us to see it. The wavelength of this waveform is 220 nanometers. So that's below the minimum that we need to see it. So we're not going to be able to see this wave. And that's really all that there is to it. Now that we've got these basic characteristics of waves, let's see what we can do about describing the motion of the wave. So waves have motion, they're moving, whether they're made of mass or energy. Most waves are a motion, and so let's characterize that motion. The time it takes for the wave to travel a distance of one wavelength is what we call a period. And because this is measuring time, we're usually going to use seconds as our unit. And we represent mathematically the period with a capital letter T. Now, I don't know why they picked T. I mean, T period, there's no T in the word period. Well, there wasn't any letter U in potential energy, and yet that's what we used as a representation. So, it's kind of like that scene from The Wedding Singer. Have you ever seen that movie, The Wedding Singer? If you haven't, you got to watch a classic movie about the 80s. It wasn't made in the 80s, but it was about the 80s. And, there's just kind of this conversation about hooking these two people up. And, Drew Barrymore, who's playing the part of the ditzy lady, she's like, well, yeah, she's single and he's single, so it makes sense, right? And so, yeah, it's like, yeah, there's period, there's no T in period, so naturally we're going to use T to represent the word period. Same sort of logic there. Anywho, if we take that period and we take the reciprocal of it, then we get what's called frequency. Now, if you remember from studying fractions, reciprocal is where you take a fraction and you flip it over. So if we take the period and we put it in a fraction form and we flip it over, then that means we're going to have frequency. And if we think of wavelength as being one cycle of motion on a waveform, then that means frequency would be how many of those cycles are we seeing per unit time. And our unit time here is typically seconds. So how many of those cycles in the waveform are we seeing every second? and that's going to be the frequency. Now, frequency measured in hertz, and a hertz, because the frequency is the reciprocal of the period. So if we measure period in seconds, then that means a hertz will be 1 per second. And we represent it with the script lowercase letter f. So that means that frequency, the letter f, is going to be equal to 1 over t. It's the reciprocal of the period. That means if we take the reciprocal of frequency, we get the period. Period t is going to be equal to 1 over the frequency. The same thing with the units. So units of frequency is a hertz. That's equal to 1 per second. We flip that over. That means 1 second is going to be equal to 1 per hertz. Remember back when we were studying mechanics and we talked about the speed or velocity of object as the distance divided by the time. Let's take that concept and apply it to wave motion so we can determine the wave speed. So the equivalent of distance for waves is wavelength, and the equivalent of time is the period. So speed is going to be wavelength divided by the period. But since the period is the reciprocal of the frequency, I could also take the wavelength and multiply by the frequency, and that would also give me the speed. And that's typically the more common way that you're going to see this described as we go through the course. The velocity is equal to the wavelength lambda times the frequency f. There's two main types of waves, and you can see them here in the picture there on your screen. So you've got a spring that's attached at one end to the wall, and we take a hand out, and if you ever played with a slinky, you know exactly what's going on here, okay? So you fix the one end, and then there's two ways you can make the wave. You can either oscillate it back and forth, or you can oscillate up and down. Either way, the wave is going to be moving back and forth. So the two types of waves that we have are relative to which way are we actually oscillating in order to make the waveform move. First way is with a transverse wave, and this just means that the oscillation is perpendicular to the direction of motion. So the wave that you see there on the bottom is a transverse wave because we're oscillating up and down, but the wave is moving left and right, back and forth. So we're actually moving the wave perpendicular to the way that we're oscillating it. Another type of wave is a longitudinal wave. Longitudinal waves oscillate along the direction of motion. So up at top where we're moving the spring back and forth, the wave that you see there is moving back and forth. So it's along the same direction, and that means we have a longitudinal wave. Musical instrument strings and electromagnetic waves are good examples of transverse waves. The oscillation is perpendicular to the direction of motion. On the other hand, sound waves and P waves that are generated by earthquakes, these are good examples of longitudinal waves. They oscillate in the same direction as the wave is moving. Have you ever been to a sporting event and seen people do the wave? Or maybe you even been in that situation where you were a part of the wave. Well, what type of wave would that be? Would that be an example of a transverse wave or a longitudinal wave? And yes, I want you to actually give me an answer. What do you think this would be based on what we just discussed? Is it transverse or longitudinal? Well, I hope you just said transverse, because that's the right answer. It's a transverse wave. Now, why is this a transverse wave? Again, I'm hoping you're actually saying something right now, giving me an answer. Why is this type of wave a transverse wave? Well, I hope you're saying something along the lines of the wave is oscillating perpendicular to the direction of motion. So, the wave is made by people bobbing up and down, while the wave itself is moving left and right. That's perpendicular to the direction of motion. That's what makes it a transverse wave. Now, you can have more than one wave at the same time in the same space. And when that happens, you get what's called wave interference. So you've got two waves that are interfering with each other, and that's why we call it wave interference. Now, this results in what's called an interference pattern. And the way we determine what the pattern will look like is by the principle of superposition. And that's just fancy math talk for you take the amplitudes of the waveforms and you add them together. So we've all seen this. If you've ever dropped two or more stones near each other in the water, it provides a good example of a wave interference pattern. Now, wave interference has two extremes to it. On the one hand, you could have what's called constructive interference. This means that your waveforms are in lockstep with each other, and so the amplitudes are going to combine to form a resultant wave with even greater amplitude. And it's an effect called reinforcement. And it's easy to see why. In this example here, look at this first crest right here is right in line with this crest right here. So when I add these two waves together, this amplitude gets added with this amplitude, and the result is an even larger amplitude for the resultant wave. That's why it's called reinforcement, because the one is reinforcing the other. And that's the one extreme. Now, on the other extreme, you've got what's called destructive interference. This means that your waves are out of step with each other, and so the amplitudes combine, and if they're 180 degrees out of step, they cancel each other out. It's an effect that we call cancellation. And this is what we mean when we say that waveforms are out of phase. They're not lined up. So here in this example here, see how the one waveform is moved over, so now the crest doesn't match with another crest, it matches with a trough. So this amplitude is the same as this amplitude, but this amplitude is positive, this one's negative because it's below the baseline. So this one's negative, this one's positive, the same number, you add them together, you get 0. Same thing here, this trough cancels out with this crest, you add them together and get 0. And that's why it's called cancellation, because each wave's canceling each other out. And that's what we mean when we say waves are out of phase. Now, this happens only when you're 180 degrees out of phase. These are this, because that's just the other end of constructive interference. Now, obviously, you could have waveforms that are out of step, but not 180 degrees with each other. And that means you're going to be somewhere in between those two extremes that we just described. So you're going to have regions where the waves are in phase, so you're going to get some reinforcement. And then you're going to have regions where the waveforms are canceling each other out, so you get 0, and you just go back and forth between this. So the result is actually a muted, actually it's a muted mutation of the two waves there, because they're out of phase, they're not lined up with each other. This brings us to what's known as the Doppler effect. So if you've got waves that are being generated by a moving object, then what you're going to get are waveforms that are closer together ahead of the object and farther apart behind the object. So if you imagine somebody who's actually stationary, not moving, and you're listening to the receiving the waveforms that are being picked up, and this is most noticeable with sound waves, you're going to get more wave fronts ahead of the moving object, and you're going to get less of them behind the object. This is what's known as the Doppler effect. So the frequency is going to be greater ahead of the object, and it's going to be less behind the object. Now, this doesn't at all change the speed of the wave, and here's why. As we just learned a moment ago, the speed of the wave is the wavelength times the frequency. Well, if you change the wavelength, you're also going to change the time it takes to travel that distance of the one wavelength. So you're also going to change the frequency. So if the higher frequency from getting more wave fronts, that means you're encountering a shorter wavelength. So you're going to get the same wave speed as you do if the source of the waves weren't moving at all. The higher the frequency, the lower the wavelength. The lower the frequency, the higher the wavelength. So it all comes out to, when you multiply together, you're going to get the same number. It comes out, and the wave of the wave speed's not going to change because of its Doppler effect. This leads us to what's called bow waves. So bow waves are two-dimensional interference patterns that occur when a source is moving at a speed greater than the speed of the waves it generates. So a good example of bow waves comes when you're looking at boats. So a boat moving on the water generates a bow wave in its wake because the boat's moving at a certain speed and the waves on the water that it generates are also moving at a certain speed. So when the boat is moving at a speed that's less than the speed of the waves that it generates, then you get a pattern on the water that's much like what you see there with part A of the graphic. So that smaller circle is where the boat's located, and the wave pattern just generates out from there. Now, as the boat picks up speed, when it equals the velocity of the waves, then you get the wave fronts there on the far end touching each other. And as you keep increasing in speed, you'll notice that the tangents of the circles from the waveforms that are formed, they actually come out and they form this V shape. And that V shape is what we call a bow wave. You can see the bow wave there in the photo of the boat. If you just look at the waveform behind and notice the V shape there on the edge, that's the edge of the bow wave because the boat is traveling faster than the waves on the water that it's generating. This is what we call a bow wave. Now, of course, this is a two-dimensional phenomena because you're looking at the surface of the water, which is a two-dimensional surface. You can actually go 3 dimensions with that, and when you take your bow wave 3 dimensions, then you get what's called a shock wave. So a shock wave is just a 3-dimensional bow wave. So instead of a V shape on a flat surface, you get because you're in 3D now you're going to get a cone, because you're looking at the edge of spheres instead of circles. And so what you're going to get is this shock wave that you see here. So here's an example that you see here with the bullet, going through I guess a board is what it is, and you're running through. And you notice how the wave occurs in pairs. So you've got a wave on the front and you've got a wave on the back. So the front of the moving object is forming the first part of the wave, and the rear of the object is forming the other part. So the shock waves are actually occurring in pairs. And there are pressure changes at each of these two wave fronts. That's what's actually causing the wave fronts. Differences in pressure from the surroundings. So the one that we see up front is an area of overpressure, and the one that we see at the back is an area of underpressure. So the one at the front, the overpressure, means that the pressure there is well above the atmospheric pressure, and the underpressure then, of course, is we're falling well below the atmospheric pressure. So maximum overpressure up front, maximum underpressure behind. And these two pairs combined to balance out and form the shock wave that you see there in the photo. You get the same effect with supersonic jets. So you can see an example here of a shock wave being formed in the air. The jet is actually traveling faster than the waves that it's generating, and that's what creates the shock wave. And then, of course, my all-time personal popular favorite example of shock waves, Superman. And in particular, Lego Superman, because of course, of all the Supermans, Lego Superman is the best. And that brings us to the end of this lecture. Hope you found it helpful. Thanks for watching, and we will see you in the next video.